Hi, my name is Cenk Ozdemir, and today I will be talking about 3.5 Nano-Ridge Waveguide photodetectors that are epitaxially grown on 300mm silicon wafers. I'm a PhD student at IMec Leuven and also affiliated with Ghent University in Belgium. 3.5 devices offer all active photonic capabilities due to their direct bandgap and also tunability of this bandgap. And compared to other integration methods, monolithic integration of 3.5 on silicon will enable high throughput and high density of 3.5 devices on silicon. Those can be co-integrated on a major silicon photonics platform later on, extending that platform's capabilities. And here we report the first indium gallium arsenide multi-quantum well Nano-Ridge waveguide photodetectors that are grown on a 300mm standard silicon wafer with low dark currents of 10 picoamp at -1 volt and also internal responsivities of 0.48 amperes per watt at 1020 nanometers. Direct growth of 3.5 on silicon is challenging due to the lattice thermal or polarity mismatches between these two materials. By applying a method called aspect ratio trapping, we can have the misfit defects arising from this 3.5 silicon interface that are trapped in this narrow oxide trenches. So at the end, we will have a high quality 3.5 at the top and also a very close proximity to the silicon substrate. And beyond, we have, with the method called NanoRidge Engineering, 3.5 geometry and composition can be precisely controlled during this epitaxial growth of 3.5 material. By applying this so-called NanoRidge Engineering method, we have grown on a 300mm standard silicon wafer a stack of PIN gallium arsenide diode. This stack has 3 indium gallium arsenide quantum wells embedded in intrinsic gallium arsenide, and this quantum wells have 26% indium composition. This corresponds to an expected bandage around 1080 nanometers. This NanoRidge is further capped with indium gallium phosphide for passivation, and a P gallium arsenide fin at the top is regrown to further displace this metal plug away from NanoRidge model fields to reduce metal losses. These devices are processed in IMec's 300mm CMOS line. We started with defining a trench with shallow trench isolation, and later this is anisotropically etched to expose silicon's 111 facets to be ready for ART and NRE 3.5 grow. And next we grown our 3.5 stack for Nano-Ridge waveguide photodetectors, and later on we exposed P gallium arsenide on the top to grow this P gallium arsenide fin, and this is finished with contact plug formation and 2-level backend metallization of the structures. Electrolytic measurements of the Nano-Ridge waveguide photodetectors are done with edge coupling of the light. So for this, 7 different dies are cleaved on one facet to produce 100 micron long edge coupled Nano-Ridge waveguide photodetectors. And each die consists 3 different 150 nanometer trench width devices, and those are exposed with a light of 1020 nanometer single wavelength laser. This light is coupled with a lens fiber with 2 micron mode field diameter into the nano-ridges. When we compare the model volume of the focused beam emanating from lens fiber of 2 micron mode field diameter and the modes inside the Nano-Ridge waveguide, they are still quite distinct by the size. So for evaluating internal responsivities, we still need to have a good idea of how much is the coupling efficiency between these two. So for this we used Lumerical's FTDD tool in 3 dimensions, and the coupling efficiency between these two we found 0.175. When we first look at the current voltage response of these devices, under no illumination, we clearly see this more than 7 orders of rectification of these diodes. And under illumination, we clearly see that the photocurrent response is clearly dependent on coupled light power. When we look at the dark current results in this aggregated box plot figure, we see that at minus 1 volt, we have 10 picoamps of dark current, and this is going up to 1.7 nanoamps at minus 5 volts of bias voltage. When we put into the sizes of these devices, we end up with 1.43 10 to the minus 5 amperes per centimeter square equivalent dark current density at minus 1 volts, which is lower than the lowest reported 3.5 photodetectors grown on silicon, and also 3 orders lower than typical germanium on silicon photodetectors. Here we have to also stress that these PDs that we compare with having lower band gap compared to our case. When we look at the internal responsivities, we need to first calculate the coupled power into the NanoRidge waveguides, which is done by the coupling efficiency we found in the FTDD simulations. And from this, we can also calculate the internal responsivity and internal quantum efficiency. In this aggregated box plot figure, as you can see, at minus 1 volts, we have 0.25 amperes per watt internal responsivity, which goes up to 0.48 amperes per watt at minus 5 volts. And this measurement has been done at 1020 nanometers of the laser wavelength, as mentioned before. And this corresponds to 30% of internal efficiency, internal quantum efficiency, which goes up to 58% at minus 5 volts. When we look at the power-dependent photocurrent response, we see a nice linear dependence with the coupled power on the light current that has been generated, and this linear fitting slope is actually giving us the responsivity, and in this case it's the internal responsivity since we correlated with the coupled power. And this fitting value, the slope of this fitting is in a good agreement with the calculated responsivities that I reported earlier. In conclusion, we report the first gallium arsenide NanoRidge waveguides with 3 indium gallium arsenide quantum wells that had operated as PIN waveguide photodetectors. These structures are monolithically grown on 300mm silicon wafer, and they exhibited low median dark currents of 10 picoamps at minus 1 volts, and they reached up to 0.48 amperes per watt median internal responsivities at minus 5 volts at 1020 nanometers of operating wavelength. This work shows the potential of 3.5 NanoRidge structures as waveguides photodetector devices directly grown on silicon, with the outlook of tuning of the band gap for desired range of wavelengths, and also evanescent coupling with a silicon photonics platform in the future. I'd like to thank you all for listening, and I will be happy to answer any of your questions.